Greetings everyone, this is Mr. Mullen. In this podcast I'm just going to go through the rest of example problem 2. This is very similar to example problem 5.2 from the book. It's just in this problem here I'm getting rid of all the numbers that we know and trying to come up with the expression for the tension in the cable. So a wrecking ball with a mass of m hangs from a cable. Prior to swinging is pulled back to an angle theta by a second horizontal cable. You can notice my little drawing here. It says, what is the tension in that horizontal cable? That's what we're looking for. So once we've done this, we need to identify the forces acting and in what direction. And so AP wants us to label these forces and draw them in the right direction. So the weight force that the earth is pulling on the ball is going to go straight down. The tension of the horizontal rope is going to be pulling in the direction of the rope, and so directly left. And then the tension in rope 2 is going to be pulling up and to the right at the same time, so it's going to be at this diagonal. Okay. So force diagram is done. Now what we need to do is we need to mathematically deal with this, and we're going to use the fact that it's not moving to help us identify what these forces are. So I'm going to redraw my force diagram now, and I'm going to rewrite some things. I know weight is equal to mass times gravity. I only have one mass I'm dealing with, so I'll just call it m. I don't know this tension. I'm going to call this T1, and I'm going to go ahead and draw my other one on here. This was T2. Okay, that was my tension 2. And so what I need to do is I need to choose a coordinate system, and so I'm going to choose x to be horizontal and y to be vertical. And the reason why I'm doing this is because I want to choose a coordinate system where I have to break as few vectors as possible into components. If I choose x and y in this direction, then I only have one component, one vector t2 that's not on these axes. If I choose a different coordinate system, I may have to break more than one vector into components, and I want to keep my life easier. If I have objects that are on ramps, typically we'll make the ramp the x-axis. But in this case, I'm just going to choose my horizontal and my vertical to be my x and y. And so that means I only have one I need to break into components, and that's T2. So I'm going to break T2 into components. That rope is pulling to the right, we'll call it T2x, and up, we'll call it T2y at the same time. So I've now decomposed that into components, and looking at my little picture, it is theta, it's pulled back theta. Okay, so it originally hangs straight down, it was pulled back theta. So now what I can do that I have theta, knowing the sides, I'm going to break T2x and T2y into components using trig. So my hypotenuse is T2, Ty is the adjacent side, so we're looking at a cosine of theta, and T2x is the opposite of that angle, so I'm going to do T2 sine of theta. So I've gone ahead and broke that part into components. Now, as I'm looking at this problem, it says it hangs and it's pulled back, so I'm going to assume that it is not accelerating. So my a sub x is 0 and my a sub y is 0. What that means then is that my net force in the x direction is 0, and my net force in the y direction is 0. That means forces must be balanced because there's no net force. So I'm going to go back and I'm going to draw congruency marks. In the x direction, all forces acting in the x direction must be balanced. And I look at my problem, and there's only one force here, tension, is in the x direction, and in the x direction the other way is the x component of the other tension force. Those have to be balanced. And then I look at vertical forces, and mg, because it's not vertically accelerating, the net force in the vertical direction is 0, so those have to balance, all vertically acting forces. Now the tension force is acting horizontally and vertically, so I'm just going to look at the component there. So once I've done this, I'm going to make a vector equation. And I like to just say, okay, T2y was equal to mg. Okay, this is like my starting point. And then this was for my y direction. In my x direction, I have acting T1 is equal to T2x. I'm just taking my congruency marks and I'm making little equations out of them. Now once I have these equations, I can rewrite these knowing what I know about the trig. So I'm going to rewrite T2y as the component that I have. So T2 cosine of theta is equal to mg. And then I'm going to write T1, and I'm going to replace T2x with whatever T2x was. T2 sine of theta. Okay, so once I have these, I'm looking for T1, but I have two unknowns here, or I have a lot of unknowns here. So what I want to do is I want to, because I know what this expression over here has T2 in it, I'm going to get T2 by itself so that I can plug it into this equation. I want to get T1 by itself. Because I don't know T2, I'm going to leave that alone. So I'm going to divide both sides by cosine theta, and T2 is equal to mg divided by cosine of theta. So now that I have that, I can plug it back in here. T1 is equal to mg over cosine theta times sine of theta. And I can rewrite this now. If I look at sine and cosine, I'm going to use trig identity. Sine over cosine is tangent. So I'm going to rewrite this as T1 is equal to mg times the tangent of theta. So there's an expression. If I know the angle and I know the mass of this object, I can quite easily find the tension in that force, in that string. Okay, this has been a really quick way to show you how to mess around with these equations without having numbers, and I hope that this was helpful.